So we now move on to descriptive statistics. So if we start with central tendency, so central tendencies are numbers that describe what is average or typical of the distribution. They describe the data you collected in a numerical form. This leaves no room for interpretation at this point, as the data is simply described. There's no explanation to it. Dispersion is how spread out the data is, and dispersion will be discussed a little bit later on in terms of range, into quartile range and standard deviation. So the focus at the moment is central tendency in terms of mean, median, and mode. So if we start with the mode. So the mode is the most common value that occurs in a set of data. So this is usually in nominal data. Sometimes you can have multiple modes. So for example, if you're looking at the mode from a frequency graph, such as like a histogram, you can sometimes have what is called bimodal data, which is where you have two modes. So of course, if you have a frequency group that's the frequency is 3 and another group that is 3, then that both of those are most common value. And then you might also have two frequency groups that have a frequency of 4. Therefore, both of your modes, you have multiple modes, so 3 and 4 would be both of your modes, making that data bimodal. So that could be a limitation potentially if you only want a single figure, then the possibility of that being used in frequency data may not be as likely, as you potentially don't want your data to be bimodal. Additionally, continuous data is less likely to have common values, as decimal places are a lot more specific, so therefore you're less likely to have a mode at all. Moving on to the median then. So the median is the middle value. So this is established after you order your data into rank order. So if n is even, the median is between two values. And if n is odd, so n is the number of participants. So if n is odd, you do n plus 1 divided by 2, and this gives you the position of your median. So you would count along and find that position, and then whatever value is in place of that position is your median. Limitation of this is that the median might not represent the data particularly well. It's just a middle number. It doesn't show. You might have a really wide spread of data or a really concentrated spread of data. It's difficult to tell based off of the median. However, the median is less affected by outliers because it is just that middle number. Median is also really good with ordinal data, but it can be slow to calculate, especially if you have a large sample size. It's not really ideal with small data sets because it's not really that relevant when you have a small data set where you can see all those individual values anyway. The last one then is mean. So the mean is basically where you add all the values together and divide by how many values you have. So it accounts for every value. This could actually be a limitation of it, because that means that all values are included, therefore it is quite susceptible to outliers, and it will be highly affected by outliers. Repeated samples tend to have similar means as well, and means are only really used for continuous data. A simple way of describing the mean is just the average. Most people would refer to mean as the average of data. When presented in the descriptive statistics of research, mean is usually presented alongside standard deviation. So, for example, if the mean was 34, it would be, and the standard deviation was 9, this would be presented as 34 plus minus 9. 34 being the mean, 9 being the standard deviation. They're often presented together just to show, because they're very closely related, obviously, because standard deviation is a direct link to the mean, because it's how far the values deviate from that mean. Therefore, they're usually presented together. So this is where we move on to dispersion then, so how spread out the data is. So range and interquartile range can be linked quite closely together. So we mentioned range before as being basically the difference between the largest value and the lowest value. And you can see here that I've worked an example to show both the range and the interquartile range. So the range here, to find the range, you would do 63, which is the largest value, minus 41, which is the lowest value, and that gives you 22, which is the range for this set of data. You can see that to make that easier for myself, I rearranged my data into rank order to make it easier to establish the smallest value and the largest value. So the range is best used for symmetric data. The range is fairly easy to compute. As soon as you've got that highest and lowest value, it's very easy to calculate. It's also pretty good for ordinal data as well. However, the range doesn't use all of the data. It doesn't account for any of the other data apart from the highest value and the smallest value. So therefore, it's very affected by outliers. So you really need to account for those outliers and the possibility of outliers affecting that range. The interquartile range is what we mentioned previously for those box plots. So it's that middle 50%. Interquartile range ignores outliers, which is one positive, as it means that it won't be affected by those outliers. And the interquartile range is basically the difference between the upper and lower quartile. So to calculate this, you have to calculate a few things. So first you would calculate the range, which we have done here, which is 22. And you would also calculate the median. So I previously said that the median, in the case of an odd number, you would add 1 and then divide by 2. So we had 15 here, and we added 1 to make it 16, and then divided 16 by 2, which is 8, which means it's the 8th position. So you count along to the 8th position, and that median therefore was 45 in this instance. You then establish the lower quartile. So to establish the lower quartile, you do n plus 1 and divided by 4. You establish the upper quartile, which is the lower quartile multiplied by 3. And then to establish the interquartile range, you do the upper quartile minus the lower quartile. So in this case, the lower quartile was the 4th position, which was 42. The upper quartile was the 12th position, which was 50. So in that case, you would do 50 take away 42 which gave you an interquartile range of 8. Like mentioned before, obviously you have to have it in rank order before you do any of this, otherwise all of your numbers are going to be completely wrong. Your median will be wrong, range be the same, but it'd be harder to distinguish, but the upper quartile, lower quartile will be wrong as well, which would affect the interquartile range. But to sum it up, interquartile range is upper quartile minus lower quartile, and those calculations are shown on the page there. The standard deviation is slightly more complicated in terms of calculations, so there's a very specific formula which you can see here. So basically, it's standard deviation is the square root of the sum of, and then open bracket, x minus the mean, close bracket, squared, over n minus 1. So n is obviously the amount of participants. So I also have a worked example for this as well. So I started by calculating the easier parts first. So I did n minus 1, which n in this case was 14. N minus 1 therefore is 13. And then you can obviously see that the table has been split into, you have the raw data, which was resting heart rate, and then you use that score. So you do this for each individual one. You take the score and subtract the mean. So obviously you have to calculate the mean first for this. And then in the column after that, you have that previous answer squared. So for example, for the first one, you had 83 as the raw data. You'd had 83 subtract the mean, and that result was 10.71. And then in the last one, in the last column, you'd square 10.71, and that was 114.70. You go through and do this for each of the values or each of the scores that you have from your data, and then you have a total. So you'd achieve a total. The most important one is the total of score minus mean squared, which was 1458.80. This is shown in the highlighted yellow column, row, and obviously the mean that we've been using is highlighted through the green row as 72.29. So if we refer back to the equation then, we've achieved both the sum of x minus m squared, as we have now the total of the score minus the mean squared, which we said was 1458.80, and we also have n minus 1, which we previously calculated as 13. Therefore, we can do 1458.8 divided by 13, which will equal 111.91. All that's left to do is to square root that. So the square root of 111.91 is 10.58, which will equal the standard deviation in this case. And obviously I mentioned previously that standard deviation is basically just how much the values deviate from the mean of a set of data.